Hello, my name is Sophia Deerdorf. This is homework 1, part A, question 1. We will be deriving the basic statics equation of dp over dz equal to negative rho times gravity. We can set up a diagram as a tank filled with a liquid. Fully submerged in the liquid is a box. This box we can pull to the side and label our forces and dimensions. This is known as dx, this is known as dy, this is known as dz. I'm going to switch colors and label a positive sign convention going upwards. We can do a negative pressure and a positive pressure on the tops and bottom of the box. The bottom one we can label as dz. The top one we will label as z plus dz. So that'll be referring to the difference in pressure between the points. Next, we can begin to label our forces. We have a force due to gravity, we have a force due to dz, and we have a force due to dz plus z. Force of gravity is going to be a downwards force of negative rho times gravity, constant, and multiplied by the differential volume. For our force at the bottom of the box, we will do the pressure of dz times the differential area. For the force at the top of the box, it will be the pressure of z plus dz times dA. All right, now we also know that the sum of forces in a static equation are going to be equal to 0. So we can set 0 equal to our force of gravity. Switch to eraser. Negative rho g dv plus a p dz times dA. And then I labeled this incorrectly here, but that's also a negative because of this downward force. So minus pz plus dz times dA. So doing some algebra, we can simplify to dA times the pressure differences. This can be rewritten as differential pressure, which is the difference in pressure from the top and the bottom of the box. Rewriting again, we can do we can cancel the dA and the dV. Well, we can cancel the dA from both sides, which will be dz, and that one will cancel entirely, so dp. We also know that this is a negative because there will be more pressure at the bottom due to static principles. So I rewrote this. Here. Again, following simple algebra steps, dp is equal to negative rho g dz, and dp over dz is equal to negative rho g. And this is our final equation. All right, moving on to question 2, we are given that the density and acceleration due to gravity are constants, and we will be deriving the hydrostatic pressure relative to h for a similar scenario as last time. Starting the same way, we can draw a picture with liquid level h we can define this as 0 and then going down to a negative h at the bottom, because we define our upwards direction as positive. Using our basic statics equation of dp over dz is equal to negative rho times g, we will move this to the other side using multiplication and rewrite as dp equal to negative rho g dz. Our next step here will be to integrate. We will integrate dp prime and set our top limit as p. We made it prime, so they're not the same variable. And set this equal to negative rho g integrate dz. We move our negative rho and gravity out front because they are listed as constants in the problem. We can define this limit as 0 and going to negative h as I showed here. And then integrate. So for the left side of the equation, we get p, and you would do like this, which simplifies to p minus 0, which is equal to p. The right side of the equation will be similar. We will do negative rho g times z. Sorry, my thing switched to eraser. And this limit will be negative h and 0, which when you plug these variables in, you will get negative p times negative h minus p g 0 is equal to, this cancels and these turn positive, so you will get positive rho gh. And then when you combine them back into this form here, we know that p equals positive rho gh. Again, box this in as the final answer, and that is our hydrostatic pressure expression. All right, for question 3, which is finally the last part of homework 1, part A, we will be given that there's a constant W and H for an above ground swimming pool, and we have been asked to find the horizontal force on the wall. We can begin by drawing a picture of the pool with height of the water, and then a side profile, height, and width. Okay, because we're finding the forces on this wall, these sections can be labeled as dz. Our next step can be to write the equations that we know of. Force is equal to the pressure times differential volume. Derive the differential force of being equal to pressure times differential area. And then we can note that P from our previous problem is equal to rho g h, or in this instance, we will label it z for terms to match our variables here. But z is just the here. So rho gz, and then we can find our dA as being equal to W times dz, or a cross section of the z dimension. So times W dz. Now our equation will simplify to this. Okay. Now from here we will integrate. We can set up df and find from the 0 to the force, which runs into a problem of having the same variable, so we can make this prime. And set it equal to rho GW. These can be pulled out of this because they are constants. So rho GW, integrate what is left, z dz, from 0 to h. Okay. I should label a sign convention as negative being down. And this bottom part, 0, h. All right. Is that right? Yeah. So then we arrive at the integration step of being f is equal to rho GW, and then z dz, its integration would just be z squared divided by 2, and this part will be plugged in from h to 0. Now we know that the 0 will cancel because when you multiply by 0, 0. So we have our final equation of substituting the h into the z, and it will be f is equal to rho GW times h squared, all divided by 2.